Shepherd Bridge, a striking new addition to Footscray, spans the Maribyrnong River along Footscray Road. This innovative pedestrian and cycling bridge enhances connectivity, providing a vital link for cyclists and walkers between Footscray and surrounding areas. Its contemporary design complements the urban landscape while promoting sustainable transport options in the community. Constructed with a steel Shepherd Bridge is a feat of engineering, weighing an impressive 450 tons. The installation process was a spectacle in itself, requiring 3 cranes over 2 weekends to lift and secure the bridge in place. The event drew the attention of local residents, eager to witness the bridge's assembly, which was completed in less than 90 seconds. This impressive speed showcased not only the precision of the construction team, but also the importance of modern engineering techniques. Beyond its functional purpose, Shepherd Bridge is designed to be visually appealing, with a sleek, modern aesthetic that reflects Footscray's vibrant character. It provides stunning views of the river and the surrounding environment, making it a pleasant experience for users. The construction of the new A40 Rhein bridge in Duisburg marks a significant engineering achievement, set to become Germany's longest-span cable-stayed bridge with a remarkable span of 380 meters between its pylons. Initiated in early 2020, this ambitious project exemplifies the intricacies of modern bridge construction, which demands planning, precise execution, and efficient logistics. The construction process involves simultaneous work on both banks of the Rhine, where the substructure is developed using robust concrete abutments and piers. A notable feature of this project is the innovative use of free cantilevering steel box girders, which play a crucial role in the bridge's stability and design. As the project progresses, the steel superstructure is longitudinally shifted along the substructure, allowing for a seamless integration of the bridge components as they extend over the water. From March to November 2022, a pivotal phase of the project unfolded, focusing on the assembly of the pylons and the installation of stay cables. This stage was critical as the pylons were erected and steel cables were tensioned, ensuring that the bridge sections, which project over the river, are securely supported. The construction team faced the unique challenge of transporting gigantic steel sections over the already completed parts of the bridge. These sections were installed piece by piece, gradually progressing until both sides of the bridge met in the center of the river. Structure was in place. The final step involved laying the roadway atop the bridge, completing the connection. This process not only highlights the technical prowess required in modern bridge construction, but also symbolizes a vital infrastructure development for the region, promising to enhance connectivity and accessibility across the Rhine. The A40 Rhine bridge stands as a testament to engineering excellence, combining functionality with cutting-edge design in one of Europe's bustling transport corridors. The Nissibi Bridge, known in Turkish as Nissibi Köprüsü, is a remarkable engineering achievement in Turkey that symbolizes not only the region's infrastructure development, but also the capabilities of Turkish engineering and labor. Located in southeastern Turkey, the bridge connects the provinces of Adıyaman and Şanlıurfa, providing a vital link between these two significant regions and enhancing transportation and commerce. The construction of the Nissibi Bridge is set against the backdrop of Turkey's ambitious Southeastern Anatolia project, GAP, which aims to improve the socio-economic conditions of the region through the development of agriculture, energy, and infrastructure. This area, with a history that dates back thousands of years, has seen various transformative projects, but the Nissibi Bridge stands out as a modern marvel that integrates local resources and expertise. The planning phase for the Nissibi Bridge began in earnest in 2011, when the General Directorate of Highways in Turkey recognized the need for a more efficient connection between Adıyaman and the surrounding areas, especially in light of the delays caused by ferry crossings over the dam lake, created by the Atatürk Dam. This situation not only disrupted local transport, but also negatively impacted trade and tourism. The necessity for a reliable and efficient route led to the initiation of the bridge project. In 2011, the tender for the construction of the bridge was announced, and Gülsen Holding, a prominent Turkish construction company, won the bid. The groundbreaking ceremony took place in the summer of 2012, marking the official start of construction. The Nissibi Bridge is noteworthy for being Turkey's first first cable-stayed bridge constructed entirely by Turkish engineers and workers. The design features a main span that is 217 meters long and a total length of 712 meters, making it one of the longest bridges in Turkey. The bridge is designed to withstand seismic activity, as it is located in a region known for earthquakes. The construction was planned according to the worst-case seismic scenario, ensuring that the structure would remain operational even after significant tremors. The construction process involved the use of high-strength materials, including 6,500 tons of steel and high-performance concrete, specifically a C60 class concrete, which can support loads of at least 600 kilograms per square centimeter. This exceptional strength allowed for the construction of robust pillars and segments, each weighing approximately 250 tons. One of the key aspects of the construction was the use of heavy lifting equipment, specially designed for lifting the massive segments of the bridge. These lifting operations were critical, as they required precise engineering and coordination among the workers. To lift a segment weighing up to 250 tons, the team utilized heavy lifting equipment that was carefully calibrated to ensure safety and efficiency. The construction also faced environmental challenges, particularly regarding temperature variations and their effects on the materials used. Engineers monitored temperature changes closely and adjusted their construction methods accordingly to maintain the integrity of the materials during assembly. It was noted that even a 10 degrees Celsius change in temperature could result in a 10-centimeter shift in the structure, underscoring the need for meticulous attention to detail. The project encountered several hurdles, particularly during periods of heavy rainfall that affected water levels in the dam lake. At one point, the construction team faced the dilemma of their floating platform becoming grounded due to the lowering water levels, which threatened to delay the project significantly. To counter this, the team innovatively extended the carrier beam by 17 meters to reach deeper water, thus allowing for the safe positioning of segments without compromising the construction timeline. The use of high-strength steel cables, each made up of 7 wires twisted together, further enhanced the structural integrity of the bridge. These cables were critical in maintaining the balance and support necessary for the bridge's long spans, with 80 cables working in concert to support the load. Once completed, the Nissibi Bridge significantly improved travel times between Adıyaman and Şanlıurfa. Prior to its construction, residents and travelers were often forced to use ferries, leading to long waits and travel times of up to 2 hours. The new bridge not only facilitates quicker and more reliable travel, but also promotes trade and tourism in the region, thereby boosting the local economy. The bridge's strategic importance is underscored by its role in enhancing connectivity, enabling easier access to markets, and promoting regional development. It serves as a gateway for economic activities, contributing to the overall growth of southeastern Turkey. The Nissibi Bridge was officially completed in May 2015, following 3 years of rigorous construction. Its opening was celebrated as a significant achievement in Turkish civil engineering, symbolizing progress and modernization in the region. The project demonstrated the successful integration of local engineering expertise, innovative construction techniques, and high-quality materials. The bridge was inaugurated with great fanfare, marking not just the completion of a structure, but also the realization of a vision for enhanced connectivity in Turkey. It stands as a testament to the dedication of the engineers and workers who brought it to life, showcasing their commitment to quality and safety throughout the construction process. The construction of the Nissibi Bridge represents a significant milestone in Turkey's infrastructure development. It is a symbol of modern engineering prowess, showcasing the ability to overcome challenges through innovation and collaboration. The bridge not only enhances transportation and trade in southeastern Turkey, but also reflects the aspirations of a nation committed to growth and development. The Nissibi Bridge stands as a vital link in the region's transportation network, facilitating connections between major cities and promoting economic opportunities. As it continues to serve the people of Adıyaman and Şanlıurfa, the bridge remains a source of pride, highlighting the potential of local talent and the importance of investing in infrastructure for future generations. The Hardanger Bridge, a remarkable feat of engineering located in Norway, connects the municipalities of Ulvik and Granvin across the Hardanger Fjord. Its construction process, which spanned several years, involved meticulous planning, advanced technology, and coordinated efforts from numerous teams. The bridge not only serves as a critical transportation link, but also stands as a symbol of modern infrastructure development in Norway. This detailed account chronicles the significant phases of its construction, highlighting key milestones from the initial groundwork to the completion of the bridge. The construction of the Hardanger Bridge officially began in winter 2009. During this period, extensive site preparation took place, which included blasting work to facilitate tunneling operations. The first significant breakthrough occurred in the last week of April 2009, when tunnel engineers successfully reached through the fjord in the area known as Voss. This achievement marked the beginning of an intensive tunneling phase that would continue throughout the year. Throughout 2009 and into 2010, tunneling work was carried out on both sides of the fjord, transforming the area into a bustling construction site. The tunnels included roundabouts and pillars of rock that were intentionally left as part of the central island, showcasing a unique blend of natural and engineered landscapes. By November 2009, engineers achieved another major milestone with the breakthrough of the Valvik Tunnel, followed by the completion of the Budenal Tunnel in February 2010. As tunneling efforts progressed, groundwork for the bridge foundations commenced in the spring and summer of 2009. This phase was critical, as the stability of the bridge depended on robust foundations. On October 7, 2009, the first concrete was poured for the Hardanger Bridge pylons. The construction team engaged in 50 hours of continuous concreting, ensuring that each foundation was adequately reinforced. Each pylon foundation required approximately 900 cubic meters of concrete and reinforcement, underscoring the scale and complexity of the project. The construction of the bridge pylons began in autumn 2009 and extended until spring 2011. The pylons were constructed using a climbing formwork system, which allowed them to be built in 4-meter sections. This innovative method not only accelerated the construction process, but also ensured precision and the structural integrity of the pylons. By August 24, 2010, one of the pylons reached a height of 100 meters, demonstrating the ambitious nature of the project and the engineering expertise involved. In parallel with the construction of the pylons, an anchorage system was developed to ensure the stability and safety of the bridge. This system comprised a splay chamber positioned below the pylons and an anchorage chamber situated deeper within the mountain. The design was crucial for distributing the tension forces exerted by the bridge cables, which would later support the main span of the structure. The installation of the splay saddles, essential for the anchorage system, began in early spring 2011. Each saddle was constructed from solid steel and weighed 23 tons, requiring precise installation to ensure structural integrity. Before commencing the installation of the steel cables across the fjord, both pylons had to be pulled back half a meter toward the anchorage. This temporary adjustment allowed for the accurate alignment of the steelwork necessary for the bridge's final structure. In July 2011, workers installed a suspended catwalk that spanned the full length of the bridge, marking a significant milestone in the construction process. This catwalk served as a platform for workers to conduct tasks high above the fjord, facilitating the subsequent installation of the cable system. By September 5, 2011, the catwalk was completed, allowing engineers and guests for the first time to walk across the span, providing a unique perspective on the massive construction effort. The critical phase of cable spinning commenced in November 2011, utilizing a specialized spinning wheel that transported galvanized steel wire bundles across the bridge span. Each trip allowed the addition of 8 wires to the strand, essential for the bridge's overall support system. Despite facing challenges during the winter months, including the impact of the storm Dagmar on Christmas Day, the cable installation was ultimately completed by July 18, 2012. The process involved meticulous coordination and safety measures, ensuring that each wire with a diameter of 5.3 millimeters was correctly positioned. The steel box girders, crucial for the bridge's structural framework, were fabricated in Shanghai. Mass production of these sections began in 2010, with surface treatments initiated in 2011. On September 20, 2012, the vessel carrying the steel box girders reached the Hardanger region after a 46-day journey from Shanghai via the Suez Canal. This delivery was a pivotal moment in the construction timeline, allowing for the hoisting of the girders into their designated positions beneath the bridge. The hoisting operation began on September 28, 2012, where cranes lifted the girders from the vessel and secured them to the hangars already in place. The total weight of all 23 steel box girder sections amounted to 7,850 tons, with each section weighing around 370 tons. The careful coordination of cranes and construction teams ensured that the installation proceeded smoothly and on schedule. As 2013 unfolded, painting and finishing work continued on the Hardanger Bridge, with the installation of railings and the creation of foot and cycle paths on the eastern side of the traffic lanes. The construction team worked diligently to complete these tasks in time for the bridge's grand opening. The combination of dry, calm weather and dedicated workforce efforts allowed for timely completion. Despite the complexities of construction, the bridge was officially opened to the public in late 2013, marking a significant achievement for the Norwegian Public Roads Administration and the many stakeholders involved. However, some minor work remained after the opening, primarily involving the removal of cranes from the pylons. A large helicopter was employed to assist in this task, highlighting the advanced logistics and planning that characterized the entire project. The Hardanger Bridge stands as a testament to modern engineering capabilities and the collaborative efforts required for such ambitious infrastructure projects. From the initial blasting work and tunneling to the intricate processes of pylon construction, anchorage system development, and cable installation, each phase played a vital role in the bridge's success. Today, the Hardanger Bridge not only enhances transportation across the picturesque Hardanger Fjord, but also symbolizes the innovative spirit of Norwegian engineering, serving as a vital connection within the region while captivating visitors with its stunning design and functionality. The project was completed in summer 2014, leaving a lasting legacy that continues to benefit the community and travelers alike. The Karapiro Viaduct is a striking structural achievement located on the Waikato Expressway in the North Island of New Zealand. As part of the Cambridge section of the expressway, this viaduct is notable not only for its scale and engineering but also for its role in improving the connectivity and safety of the road network in the Waikato region. The Cambridge section, stretching 16 kilometers, links the existing Tamahuri interchange and terminates approximately 2.5 kilometers south of Cambridge, where it joins State Highway 1. HEB construction began work on this major infrastructure project in September 2013, with the goal of completing it by late 2016. Along this route, the Karapiro Viaduct is a standout feature. A 200-meter-long, 40-meter-high structure that bridges the scenic Karapiro Gully. The project also includes 3 interchanges and 4 additional bridges, emphasizing the complex and multifaceted nature of this infrastructure development. The Waikato Expressway was conceived as a response to the growing demand for better, safer, and more efficient transport links across New Zealand's North Island, particularly in the Waikato region. The expressway aims to reduce travel times between major cities, improve freight efficiency, and enhance road safety. By alleviating traffic congestion and providing a more direct route, it benefits both commuters and commercial transportation. The Karapiro Viaduct, as part of the Cambridge section, is a critical component in realizing these benefits. Its location across the Karapiro Gully was chosen for its capacity to create a safer, smoother route for vehicles by avoiding steep inclines, sharp turns, and intersections that characterize some of the older routes in the area. The Karapiro Viaduct's design reflects a balance of engineering ingenuity, safety considerations, and environmental sensitivity. At 200 meters in length and 40 meters in height, the viaduct is a major engineering accomplishment that involved careful planning and precise execution. Spanning the gully required a structure that could handle the varied and challenging terrain of the area while ensuring minimal disruption to the natural landscape. HEB Construction undertook the challenge, and the company was tasked with completing the project on a tight timeline. Beginning construction in September 2013, the team encountered several technical and logistical challenges associated with building such a large structure over a gully. The construction approach involved using advanced materials and innovative construction techniques to create a resilient and durable bridge capable of withstanding the region's weather conditions and the stress of daily traffic. This included constructing deep foundations that could support the weight and length of the viaduct while remaining stable over time. The Karapiro Viaduct was designed with specific features that enhance its durability and functionality. Constructed primarily of reinforced concrete, the viaduct is intended to resist both the pressures of daily use and potential seismic activity, an important consideration in New Zealand. Its elevated design allows for the smooth passage of water and wildlife underneath, minimizing its environmental impact on the Karapiro Gully ecosystem. Additionally, the viaduct's position across the gully helps preserve the area's natural beauty by reducing the need for a wider, more intrusive road construction project that would have required extensive grading and clearing. In terms of road design, the Karapiro Viaduct includes dual lanes for both northbound and southbound traffic, which helps facilitate safe and efficient travel along this section of the Waikato Expressway. The design of the viaduct, along with the wider expressway project, reflects a modern approach to transportation infrastructure that values both functionality and environmental responsibility. From its inception, the Waikato Expressway project, including the Karapiro Viaduct, emphasized the importance of minimizing environmental impact. The gully area is rich in native flora and fauna, and the construction team implemented measures to protect the environment both during and after construction. For instance, the elevated structure allows natural watercourses to flow freely beneath, supporting the ecological health of the area. Additionally, native vegetation was preserved where possible, and restoration efforts included replanting native trees and shrubs around the construction area. The viaduct also plays a role in improving safety for local drivers and reducing traffic flow through nearby towns, which is significant for the community of Cambridge. By redirecting traffic away from more congested urban routes, the viaduct and the expressway as a whole decrease travel times and lower the likelihood of accidents on local roads. This aspect is especially appreciated by residents and businesses in the area, as it improves the quality of life and supports the local economy by facilitating smoother transport for both commuters and commercial traffic.